Okay, so I want to talk about testing, and not just about writing tests, but about designing your application to be testable. We're going to use this little toy calculator to demonstrate how that works. Basically what you instantiate a new calculator, and then you can evaluate strings, and we'll tell you what they evaluate to. If we look at the source code for this, it's just really a very, very simple recursive descent parser. And I know not everyone is into parsers, and maybe not very many of you know what recursive descent parsers are, but we'll talk about it really quick, just so you get a quick overview of what it's about. Basically, a recursive descent parser, the idea behind most parsers is you take some input and you construct, it's called an abstract syntax tree. Basically a tree of objects that represents the input you gave it. So if we look at some of these inputs over here, what we would have for this is a tree with one node that represents the number 3. This one might be a tree with 3 nodes. We would have one node that represents this operation plus, and then its left child would be a node representing 3, and its right child would be a node representing 5. And of course, these trees can get more and more complicated the more things you put in there, right? So for our parser, these 3 classes right here represent our abstract syntax tree. I'm just going to say AST from now on. The atom represents the numbers. A unary expression represents like a -5, and binary expression, that's the plus, minus, times, divide. Okay. Now, if you look, this is the grammar that our calculator parses. Down at the bottom, you've got a factor, which is either a number, a parenthesized expression, or a negated factor. See, it's recursive. A term is a factor followed by an optional operator. And that operator can be a times or divide or nothing. And an expression is a term followed by an expression operator, which is plus or minus. And we split it up like that so we can get operator precedence. But the nice thing about recursive descent is basically each of these rules on the left become a function. You implement each one of those, and then when you call the expression function, it will automatically recursively call the rest of these, and you get your parser. So our calculator has this public evaluate method, and this is the only public method on our calculator. It basically parses the string and gets the AST, and then it evaluates the AST. Parsing creates a string scanner. I don't know if anyone's ever used the string scanner class in Ruby, but it's awesome. And then we pass that scanner to parse expression. Parse expression says, okay, on the left, we have a term, right? Just like that. So we call parse term. Well, we descend down. Parse term calls parse factor. Parse factor says, okay, skip any white space, and then parse either a number, or parse an open parenthesis, or parse a negation, or error. Can't do anything with it. Okay, so the whole thing just works that way. All these different parser methods. And then when we evaluate the tree, we have this abstract syntax tree. Here we go. And a node is either a unary expression, in which case we evaluate the tree, that's the node that's wrapped by this unary expression, and send it whatever operator is defined on that, like the negative. Okay, so that's the unary negation. Binary, we evaluate the left tree, and then send node.op and evaluate the right tree. And if it's an atom, then it's just the value. And that gets called recursively and evaluates the whole thing. So that when we run it, I don't know if you can see that way down there. You can see 3 evaluates the 3. Let me do it this way. You run it, that's a little bigger. 3 evaluates to 3. 3 plus 5 is 8. 3 plus 5 times 3 minus 1 is 17. 3 plus 5 times 3 minus 1 is 16, and so on. Okay? So it works. But now when we're like, okay, we want to write some tests for this so we can know that it works, know that it's correct, right? So we sit down, we're like, okay, we'll set up, we're always going to want a calculator. Now let's make sure factor is parsed correctly. So we evaluate a factor, and we get 3, and yay, it works. Only are we actually testing that a factor is parsed correctly with this test? No. We're testing that the calculator correctly evaluates the string 3. And parsing a factor is one part of that. But this is testing the whole stack. Okay, this is like writing functional tests in Rails, right? Where you're making a call, a get to some action, and it's going to run the whole stack and come back with something. So this isn't testing that. This isn't testing what we think it's testing. It's testing a lot more. So let's try this. Let's actually call that private internal method, parse factor, with a scanner we've specifically set up. And yeah, now we get a node back and we can assert that, okay, that node is an atom and its value is 3. And that is testing that the parse is occurring. But this is still a bad idea. Any idea why? We're testing a private method. You should never be testing the private interface of your classes. If you're testing the private interface, it's because there's a contract, right? The public interface of your object is a contract that you're implicitly providing consumers of your object. That private interface can change. You're under no obligation to keep that private interface consistent. Between any given release of your code, you're under no obligation to keep that from changing. And so if your tests are basically consuming that. Your tests are clients of your public API. When you write tests for your private API, things get really, really fragile. It's generally a sign that you've architected things incorrectly if you ever have to call a private interface on your class from anywhere except inside your class. Does that make sense? Any questions about that before I go on? Does anyone disagree with me?
In practice, do you end up, I mean, I've seen, at least my experience looking at code, and I probably haven't looked at the best code, but people are pretty lazy about making things private in Ruby.
Mm-hmm. Yeah, you know what? I don't actually I'm not explicit about it either. I don't like the way it's done in Ruby. So what I do is I just prefix the internal API with an underscore when I do it. So, I mean...
You don't use the language to say this is private.
Right, because you can get around it in Ruby. Super easy.
You're a closet Python programmer.
I like everything about Python except the syntax.
Or the lack thereof.
So...
Hey, it's Lisp that has none, okay?
So I would strongly recommend that you never call these private APIs. So what do you do with your tests? Like, yeah, go ahead, Record.
Like I've had private methods that do like pretty complex things. I just wanted to test that in isolation.
Yep.
So how else do you do that?
I am so glad you asked, Riker. You totally segue right into the next one. So yeah, I mean, that's it exactly, right? You have a lot of functionality. You look at this calculator, there's a lot of functionality hidden behind this internal API. And when you're testing, you want to make sure things are working correctly. If we're only testing our public API, that means our calculator, we're only allowed to call evaluate to test it, which totally ties our hands. So the solution is to refactor. If you find yourself trying to get at a private API, it's probably because your class is doing too much and you need to split it up into smaller responsibilities. Like Riker, if you have a particular method that's doing a lot of complex stuff, it should probably be in its own class. In which case, that private API suddenly becomes the public API of that class, right? You've changed the responsibility of the class to where that is now the primary responsibility, and you can test it.
Hey, James, so I'm totally with you on breaking down classes to make them good, but what if that was originally private because you did not want it to be exposed as part of the public contract?
Okay, there's a difference between the public interface on a class and the public interface of your system. You can have a class that is internal to your system that's not intended to be consumed outside your system. And you can test that inside your system, right? So just because you take this complex method and you break it into its own class, that does not automatically mean you have to also expose that class to anyone that consumes your system.
So, other than like a couple of words, what really is the difference between saying this is a private method that I'm going to let my test access versus splitting it out and making it public? But it's not public to the rest of the world, it's only public to my test.
Saying that you should not test private methods is really just a convenient way of saying your classes should do one thing and do one thing well, right? I'm talking about the single responsibility principle from solid design principles. If your class is doing more than one thing, it complicates a lot of stuff. It makes maintenance of the class harder. It makes it harder to think about what the class does. It makes it harder to explain in documentation when people should use your class. Whereas if your class is focused on one responsibility, it's a lot easier to test. It's a lot easier to document and maintain, and describe, and think about. A lot easier to reuse, right? I mean, a robot that washes your sink and makes your bed is going to be, well, I mean, we all need to wash dishes. But anyway, one robot that does two very different things is going to be harder to reuse than two robots that do very specific things. Does that make sense? So what I'm saying is the difference between a class that's internal and a method that's internal to a class is really the idea of that single responsibility. Am I making sense?
Yeah, so really we're just using the private method as a rule, that you want to test as a rule of thumb, a guide, to say this is probably multiple responsibilities.
Right.
Okay.
Yeah, it's a red flag.
Okay.
And I'm speaking in absolutes here, but obviously nothing is an absolute, right? There's always going to be times where, well, yeah, that's the rule, and I know the rule, but in this case, the rule is wrong, and I'm going to do it this way, right?
It's like the pirate code. More like that.
More like guidelines, really.
Okay.
So in this refactoring now, we're trying to give each class one very specific responsibility. Notice that our AST nodes now have that evaluate method on them. Back with this one, if we wanted to test that evaluate, well, too bad, evaluate tree is internal. We can't test that, right? Because we've said we aren't going to test internal methods. Also, this is a red flag too. Whenever you have a big case statement that branches based on the type of its argument, that suggests that you should probably be pushing things into classes. So that's what we've done here. We've pushed that evaluate in, so binary knows how to evaluate itself by calling evaluate on its left and right, and then sending for the operation, unary and atom. So that basically makes that evaluate tree go away, and these binary expression, unary expression, and atom classes can now be tested on their own, right? I can instantiate, in fact, let's look at an example right here. I can instantiate an atom, well, no, right here. I can instantiate an atom here with a 3 and assert that when I evaluate an atom, I get a 3 back. Like that is a very atomic test, right? I'm testing one very specific thing. An atom is simple enough that I can now say, okay, now anytime I have an atom, I am sure that evaluate will give me whatever it was I passed in. Same here, I can test that unary expression and assert that, well, if I have a unary minus on some other node, when I evaluate that unary, I get negative of whatever that node was. So that's one way to break that out. Another way is to realize that the calculator was doing too much. It was parsing and evaluating. Well, parsing is a responsibility all on its own. So we can break a parser out all by itself and say, we have a class now that is responsible for parsing strings. I give it the string I want to parse, and then I say, okay, give me an expression for that. Give me a term. Give me a factor based on what's in that string. This does a lot of things for us. First of all, because these are now public interface on this parser, I can name them a bit more. Like, for instance, I've ended anything that has to match something on the input with an exclamation mark. If I call factor, it has to match something on the input. Term op, though, does not. That's the optional operator for a term. It can match a times or a divide or nothing. And so I put a question mark on that one. So now, is it a number? Is it a parenthesis? Is it a negation? Well, nope, it's none of those. So you can reason a bit more about the responsibility of the class. You can simplify it, and you can test it, right? Our parser now, I can say, let's test that an atom is parsed correctly. Well, we instantiate a parser for this string, and then we call factor on it, which gives us an atom, or it should. We assert that it is, and we assert the value that is expected. And it's all external API, all exposed API on that class. And now our calculator becomes ridiculously small. That's our calculator class now. It's still just the one public method, but it now relies on those other classes to accomplish what it needs to do. It instantiates a parser, parses an expression, and then calls evaluate on the tree. And you're good. Let's see if I'm missing anything here. So we still maybe want to call, test the evaluate to make sure that it's doing what we've told people it will do. But we're also able to have a lot more tests that can test much more granularly the functionality we want on that. Any questions about that so far? Joel?
Can you speak a little bit to how you think about evolving code? Because one of the things I'm always worried about is like, okay, I'm doing this thing, and I'm going to create 10 classes. And then I find out, oh no, actually I didn't need 5 of them. So I tend to be too refactor, right? Well, this
Yes.
thing is simple, and maybe it's got too many concerns. But once I start realizing how it's evolving, I start breaking it down. How do you think?
Absolutely. It's an iterative process. It's like that phrase, make it work and then make it right. I do that all the time. In fact, when I sat down to prepare this is literally what I wrote first. I'm like, okay, I need a calculator. So let's make something that parses and then evaluates. So this was literally my first go at this. And then I was like, okay, I knew going into it, by experience, I knew that this was going to be not the ideal architecture. So once I was done, I was like, okay, now that's a long class, right? And it's difficult to test. So how do we break it apart? That's where I then said, okay, what are the responsibilities? Where can we do that? And that's where you take the hacksaw to it and start breaking it apart. But it is iterative. It's not this is not how I work anyway. I don't sit down and say, okay, on paper we're going to draw our diagrams and all our classes and all this. Bam, there's our architecture. Now let's implement it. I think you're going to get in trouble if you do it that way. It's better to make something that works, learn the lessons you need from it, and then refactor or rewrite, depending on the scope of what needs to change. But,
Yeah, there's danger in pre-engineering process.
yeah, exactly. That's where you wind up with a lot of really heavy complexity, because you don't know the answers up front.
Balancing that, because there are plenty of problems that if you don't tackle them at least as a good concept at the beginning, you'll be going down a path that is very hard to refactor to something that's elegant.
There's something, yeah.
So the bigger the system is, I think the more you need to look at things in advance, but keep it at a high level.
Well, you need to look at them in advance. You need to understand your domain, for sure. And the more complex the domain, the more planning you're going to need. But it is iterative. Even then,
Yes.
you're going to sit down, you're going to say, this is huge. Let's start somewhere. And then you're like, okay, we learned a few lessons. Throw that away. Try again. There's nothing wrong with writing code to throw it away. That's a great way to learn a lesson. I guess it could be bad if you're under a tight deadline, but I think that's part of the cost of writing software, is learning the domain by writing it once and then doing it right. Okay. Now here's another pattern I've seen that I really want to warn you against. Maybe we want to see whether our parser is actually consuming all the input like it should. We want to make sure it doesn't leave any tokens on the string unconsumed, right? It needs to parse the entire string. So we construct a parser with something, we call this, and then we say, okay, well, we need to look at our scanner and make sure that it is reporting that it's at the end of string. Never, ever, 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 ever call instance variable get in a test, or pretty much anywhere, okay? Instance variable get is a great tool for writing meta programs, where you're needing to access some internal state programmatically, where you don't know the name of it when you're writing the program, but you will when the program is running. I don't know if that makes sense. If that doesn't make sense, it's probably because you've never encountered a need for it, and most people never will encounter a need for it. But in tests, this is just a way of saying, I don't know how else to test this besides looking into the internal state of this object. And you're violating encapsulation, which is going to get you into trouble if that internal state ever changes. Like the programmer, when they wrote that library, they had no idea that someone's going to access this instance variable. So they could very easily go in and change the name of the variable. They could refactor so the variable goes away entirely. Depending on an internal state like that is very fragile. So what you do instead, like it's reasonable. Like this is a reasonable kind of test to want to do, to say, did we consume all of the input? Well, one way to do that is to actually expose that private state for testing. Make that part of your external API, your public API, your contract that you're doing with anyone that consumes that class. Because then you can just say parser.scanner, and you're good. The danger here is you don't want to expose all of your internal state just so you can test it. Internal state is internal for a reason. Sometimes it makes sense. Like it might make sense for a parser to expose its scanner. There's times where that internal state is part of the external, the contract you're making with your clients.
Would this be a good time to have a getter function?
Yeah, that's what this is.
Oh, that is.
After reader it basically creates a getter. Yeah, Ruby, you can't actually access the variable directly without using like instance variable get to actually reach in and pluck that out. So yeah, thanks for pointing that out. Attrib does create a getter. Like I said, there's times where it's appropriate. There's a lot of times where it's not. And so what do you do when it's not appropriate to expose that? Well, you can refactor some more. The thing with the parser is it's still doing more than one thing. The parser is also scanning the input. It's breaking the input into the tokens. It's skipping over the white space, as well as interpreting the semantics of the tokens it's getting off the input stream. So another way to refactor is to split the parser even more. Notice the red flag. Let me just point this out quickly. The red flag that tells us maybe we need to split it again is this. The fact that some internal state needs to be inspected. So instead of having that be internal state, we split that out into its own class, the tokenizer, which is going to be responsible for saying the next thing is a number, the next thing is an operator, the next thing is a parenthesis, and so on. We split that out from the parser. So in our test now, we instantiate a tokenizer, we pass that tokenizer to the parser, we do whatever we need to with the parser, and then we can assert that the tokenizer is empty. We no longer have to reach into the parser to get at its internal state because we told the parser what the tokenizer was. We have access to that. That makes sense? Now, part of the art of writing software is learning to recognize these patterns. Learning to recognize when a class needs to be split and how it should be split. And the only way to really get better at that is by doing it. And that's why we do code reviews, right? So that multiple people can look at it and say, hey, I wonder if we could split this here. And everyone learns from that. That's it's pretty valuable. But no one should feel bad that, maybe they didn't look at this and say, oh, you know what? That needs a tokenizer and a parser, and if we moved the evaluate up into the AST classes, that would be cleaner. Some of you maybe did, but don't feel bad if you didn't, because a lot of it is just practice, getting better at it. And the problems you're facing in your projects are going to be very different from parsing an input stream, right? But there's still going to be patterns you can recognize. And some of those patterns, some of the anti-patterns to recognize are in the tests. There we go. If you find yourself testing too much, like trying to test one specific thing by calling a method that does a million things, that's a red flag. Reaching in and trying to test some internal interface, that's a red flag. And reaching in and trying to call or trying to access the internal state of an object is also a red flag. Those all should tell you something is wrong, even if you aren't sure what exactly is wrong. And then you can act on it. Any questions?
So through refactoring, what we've determined here is that our classes really need to remain simple and focused. So then the internal state of our classes becomes very simple and not something we necessarily need to expose in order to enable tests.
Mhm.
So is this an argument towards moving towards functional programming where we have, I mean, if our classes become simpler and simpler, then could we just start to replace our classes with functions? Because functions are pretty easy, especially pure functions are really easy to test.
Mhm.
And so if we essentially eliminate a lot of the complexity of internal state from our classes, and I'm just thinking, I'm not making an argument either way. I'm just thinking through this and wondering if that's why we're seeing a kind of a push towards that right now. Because as we become more of a test-driven, as we focus on becoming test-driven in all of our development, we try to make our code match that, right? We've tried to make it easier and easier to write tests. And so I think that has kind of given rise to this whole functional programming paradigm. And I wonder if that's kind of what we're looking at here is, yes, our classes have become very simple so that we expose a minimum number of functions and reduce complexity of internal state. Maybe
Yeah, no,
functional programming is an answer.
Yeah, well,
I think there's
I would say
something to
there's
that.
multiple reasons for functional programming, one of which is the question. And there's lots of other reasons. But there's also reasons to
Yeah. It seems to me with objects, whenever I have a class, it's because I need to maintain some state of that object. That object has some inherent state, right, that needs to be considered or evaluated or something. It holds on to that versus a function which just takes a value and returns a value.
But it is also just a
Different.
set of patterns, right? Like a lot of times you could, it's just like in Ruby we're writing classes. You're not even thinking, well, I'm not going to do it. Well, rarely. You think, let's do this with that.
Right.
But it's not because you couldn't.
Yeah.
I think there's a sweet spot. I mean, I think Justin, you're onto something there. You know that the push towards functional programming probably has a lot to do with the pressures we felt from testing. But I think there's a sweet spot. Like at some point, obviously, you could write Ruby with only functions, Ruby code with only functions and no
Sure.
classes. But I think you lose a lot of the benefits of what Ruby gives you. And so there's a sweet spot. At some point, you're going to say, well, I could split this class further, theoretically. But at that point, it starts to cost more in how much I have to think about it and what it takes to maintain it. I think there's some point where it all kind of comes together as the ideal.
Yeah, and I think mentally it's nice. Classes are nice because they mentally group things together for us. They put it in a nice little package, and it's really easy to reason about that package. So I think the perfect example would be active record. With models, I don't know that I would want a whole collection of functions that I would have to call every time I wanted to deal with the database. And active record, encapsulates that experience and makes it really nice and really simple. And so even though active record actually gives you a fair amount of complexity, I mean, the classes that you inherit from are not insignificant, right? Like there's a lot of code sitting there. So, but we take that for granted in all of the code that we write. Like I can just call .create. Wow, look, amazing things happen. So, well, no, really. I mean, like before Ruby, a long time ago, when I wrote .NET code, I wrote an entire application whose job it was to scan the database and generate classes and generate stored procedures and generate all the functions to do all of the CRUD things. But I had to do that. That wasn't given to me. And so it would output like 500 stored procedures and a number of classes based on that. And all this stuff was pre-coded. But active record, I just make a model and I just call .create and I don't have to do all that work. So it's really nice.
Before .NET.
Or pick any other,
Ye old Fortran.
back in my C days, back when I used to write assembly